तेजस्विनावधीतमस्तु मा विद्विषावहै।
We were looking at the novel algorithm we have developed for DCT quantization etc., and we saw this matrix which is the outcome of the application of DCT here on an image block. We have not shown the image block deliberately. For each of these corresponding elements, it may be anything from 0 to 255, being 8 bit for the actual pixel values, and you will be normally you will be seeing some 156, 160 like that, all around that. It may be on an average as far as the input pixels are concerned, and this is DCT is nothing other than evaluation of 3 matrices C, X and CT, and that gives final result will be 8 by 8 matrix, which is what is shown here. And the very first coefficient, as I mentioned, is the DC coefficient, and see the value is quite high when compared to all other coefficients, and that is the reason why I was saying it is 8 times the average of pixels intensities put together. And so if you divide this by the quantization matrix, the matrix is also for every 8 by 8 matrix you will have quantization matrix. The first coefficient will be 8 corresponding to this term, and 16 for this, then 16 for this, and another 16 for this, then 19 like that, it goes 22 and so on until I think 84 or some such thing. And you have to take one DCT and divide it by corresponding coefficient. In this case it will be 8, so 1260 divided by 8 and rounding it off, that is dropping after the all the fractions, what you will get is 157. It is not a rounding off, it is actually truncation. So if you want to recover this back, what all you need to do is just multiply that by 8, this value. What do you get after when you multiply? Do you get it back? No. So if you multiply this 8 into 6, 6, so I think it is 1256. So you started with 1260, but when you reconstruct, that is what is called reconstruction, you do not really recover what you have. So this is naturally quantization is responsible for this, because we are quantizing by 8. That means to say we take only every 8th value. So that is why we have here in this fashion, and this is naturally a lossy process involved, and therefore you can't really recover the actual, you can't reconstruct the actual image, but it will be an approximation of the image, but on most occasions it will be quite good. Sometimes you may be surprised to see a very good image constructed. and purpose of quantization is to create as many zeros as possible, that is what we have mentioned before, and which need not be encoded in VLSI, variable length coding, and only these non-zero coefficients are actually coded and converted into serial bit and sent over the as a bit stream on the transmission channel. And this is just a sample block we have seen here. This is DCT coefficients as mentioned here, and this is after quantization. Quantization is merely division by another constant, a group of constants. So here these stages can be pipelined in such a way that one DCT-Q output can be generated every clock cycle, and this also I think we have seen there, and we will see little more later on. And once similarly inverse quantization can be computed by multiplying each of the 64 DCT coefficients by the corresponding quantization table values as per the expression. This is what we have already explained. Actually this is a quantization matrix, 8 by 8 matrix. Once again you can see UV correspond to the DCT coefficients earlier, and so here we recover the DCT portion. We start with DCT-Q, and if you multiply, earlier we divided by 8 in order to get the DCT-Q from DCT. Now we have to multiply by 8 in order to get the very first coefficient. Similarly for other coefficients 16, 19 and so on, and we will create the corresponding DCT value here, and this is the process of reconstructing the image at the receiving end, right at the decoder. The encoder decoder that we have seen before is also abbreviated as codec, and so here next step is we have still only the DCT coefficients available here. We have not yet recovered the actual image, and we can recover it only by doing an inverse operation of this, which is similar to DCT, only order is it has got to be CT into the DCT and C. These are all the once again 8 by 8 matrices, 3 matrices, and the parallel algorithm we have done before is equally applicable for this IDST as well, and outcomes 1 pixel per clock, that is the throughput that you can get here, and it has got to be the same rate as the DCT creation, and same algorithm works here too. So now we will really start going into the design, and before we design any system that you want to design, so you will have to first have a overall bird's eye view. So for example you want to ultimately do a chip, so why not a good starting point will be to put a black box and then label this is the design for DCT quantization, and as mentioned here, and what we are going to formulate is the specification. And now in order to communicate the image, what signals you will be requiring, let us examine that. See for example I can use a host processor in order to communicate this signal, I mean image, and this we need a very high throughput. So we can think of using a parallel bus such as PCI bus, which we have already had a glimpse when we did PCI arbiter earlier, and we had used, I mean any block of image we can apply one row of a block at a time if you have 64 bits, and through PCI bus a 64 bit bus will be handy here, and you can use PCI signals here. And for example BE stands for the byte enabled, and there are 8 bytes here, which byte is referred here, and to enable that particular byte you need signal here. These are all basically a PCI signal, and if you have a core, naturally you need to reset at any point of time. So what we have here is reset n actually here, and this is standard in any of our designs seen earlier, and so once you have this, you can have you can communicate the image information from the host processor or from any other processor such as video grabber, which we have seen before, and into this DCT-Q, which is basically the hardware implementation after going through Verilog coding, which we are going to do shortly. and you also, in order to write different rows of a block, there are 8 such rows. So, you need a write address for that, 3 bits are needed for that, and you also need a clock such as the PCI clock. This is the host computer interconnection right from all this, and when this data is valid should also be indicated by the host, and that is by this. And once you have put in 8 rows, you can have you can write it in 8 clock pulses using this PCI clock. So, after you have written one block of information, and you can start the entire DCTQ process, and when the DCTQ process is going on, you can also input next block of image, and this DCTQ processing, there are 64 coefficients, and as I mentioned before, every clock you can have 1 pixel processed, equivalent to 1 pixel processed, and thereby you have a 64 clock cycles requirement here for processing one block, whereas you need just 8 clock cycles as far as PCI clock is concerned in order to input here. That relieves the burden of the host processor, which is dumping in the image here. So, it can attend to any other duty other than merely inputting the information here, and this is a time consuming operation. We have seen before, realization of 3 matrices is actually a very time consuming operation, and I think it is n cube times, n stands for 8, and so many computations are involved, multiplication as well as addition, and you can cross check from the matrix we have seen before. So, once you have loaded the image, you can ask this DCTQ to start the DCTQ process by this asserting this signal, and once it has started, at any point of time you can hold the processing, and thereby you do not have to bring in what is called latency, which we will explain later on, and if you use hold signal. And there is also a system clock required for DCTQ operation to churn out the DCTQ, and that clock is fed here, and when this DCTQ is ready to accept input, will be indicated by an output signal called ready, and the actual DCTQ output after evaluating will be output here, and it will be a 9-bit output, and this 9-bit output is signed, it will be in 2's complement. This is as per the requirements of the JPEG MPEG standards. So, that is what we said before right at the introduction, that whatever we design, it will have to conform to the standards. So, otherwise there is no communication from one design to another, one product and another product. And which coefficient we are referring to, is it DC coefficient or the AC coefficients? If so, what is the address? So, that question also will have to be answered. The answer is output this address for the coefficient, DCTQ coefficient, and when this DCTQ is valid, that also will have to be indicated by high going signal. So, with this you can very well design a DCTQ processor. So, from Bird's point of view, we have seen all this, and we also had used some of our knowledge about the actual host interface, such as a PCI interface. And once we have formulated here, what we had briefly explained here for each of the signal is listed here. So, this is a block diagram of DCT, and each of this signal will have to be explained here, and I will quickly explain because I have already explained. And this reset is active low asynchronous, which is a standard in our design, and input is fed through this DI. One row, that is 8 pixels of an image block, 8 by 8 pixels is input, and into this DI 7 through 0 is the first pixel, and the last byte is the last pixel in the particular row of 8 pixels. Like that, in a block you have such 8 rows, and we have to write one after another, and a pixel is of size 8 bits unsigned. So, note that it is unsigned. So, this is nothing other than X matrix in that CXCT evaluation, and so the X is complete only with 8 writes as such, because every write you write only one row of the block. So, you have this byte enable here, byte enable B0 selects DI 70 and so on, the higher order is selected by the 7, and we have seen this also, right, is the 0 is the first row address here, and 7 naturally is the last row address of the block, and image input synchronous clock, that is the PCI clock here, and D higher, I mean all the bits are written using this address, serving as the address synchronous to positive edge of this clock. So, we had to define all the signals when it really happens, whether it is positive edge or negative edge, whatever is the case, we will have to specifically spell it out. And similarly, data invalid, when the input data is valid, then we have start signal, and what they are, input or output are designated straight away here. Active high starts and maintains DCT-Q processing. Once you have started, you should not make it low, should keep it high. If you make it low, the whole thing will be suspended, and again it has to start afresh. So, every time you start afresh, you have to pay the penalty of latency. So, in this particular design, you will see that later on the latency is around 45, which is quite hefty, and why that, so we will explain later on. If deasserted and reapplied, latency will come into effect again, that is what we are saying, that this latency basically is applicable only for the very first block that we are processing. That means to say the output starts coming only after the latency time has expired, only after a delay it will start. Once it starts, 1 pixel 1 clock rate is maintained, so long as you do not make this 0. The moment at any point of time you make it 0, again that 45 latency will come into picture. So, if you want to avoid that one, a better alternative will be to use the hold, so that it freezes at the point where you left, and you can resume at a later time when the need arises by deasserting the hold. So, that is what is mentioned here. DCT-Q processing can be kept on hold, deasserting resumes the processing without any latency coming into play, and clock is the system clock for DCT-Q operation, and ready is the output signal. This indicates that the core is ready to, core in sense DCT-Q core, to accept image input block, and DCT-Q is the output in 2's complement valid positive edge of clock. Note that this clock is different from the PCI clock, that is for the inputting the image, whereas this is outputting the actually churned DCT-Q, and the corresponding DCT-Q address is furnished here. Address 0 is the DC coefficient, all others are up to 63 are AC coefficients, and when it is valid is indicated here by this, and also the validity of address here, and all these signals excepting reset n are all active high. So, this is the standard design. And now we will have a look into the architecture. So, the first step is we had to specify what we want, that is what we had done by describing different putting a block and then putting describing the signals, and they are the basic definitions. Once with this, and the undercurrent for all this is the implementation of the algorithm that we have seen before, that is the crux actually. What we are trying to do here is merely turn those that algorithm into a chip finally. So, just before prior to making the Verilog design, so we need to put a hardware structure here, and this is what is called architecture. The architecture will have to reflect the actual hardware that we need, and let us see here. We have already seen dual RAM designed earlier, and that is precisely what we are going to use here. So, I am not going in to describe dual RAM, and except for the signals merely to recollect what we had done before. So, and all this bold note are the pin configurations that we have seen before, a block diagram we have seen with all the IO pins there. So, that is what is going to be the final IC, that when you do it as an ASIC or FPGA, and those things are mentioned bold here within the architecture, because there are so many signals this in the architecture, and other than bold they are all internally created. So, it will come from some other module, and so these things we have already seen before. Input is applied here and through DI, and when it is valid byte enabled, and which row address we are talking about is here, and PCI clock at positive edge of the clock we input here, and it is a dual RAM in the sense we have 2 RAMs here, and first block that you have to put in will be put into the one of the RAMs, say RAM 1, and RAM 2 is to start with empty, therefore no DCT quantization will start, and after completing the first RAM 1 filled, so we will give a start signal, and that start signal is down below, which we will see later on, and this up to this we have seen here, and invalid is the data invalid, and you need 8 PCI clock cycles in order to write one image block. So, once that is done, we had to switch control from one RAM to another, that is done by toggling this R and W. This toggling of R and W must be by the DCTQ processor. This will be the signal internally created. You will see later on that it is coming from the controller, which we have will see here the design, and this is the system clock. And you also need in a dual RAM, you need not only to write into the RAM, but also read in order to process the DCTQ. So, unless you read, you can't process DCTQ, which will happen right from here, and for that you need again row address. So, again once again 3-bit address is required, and so the nomenclature read address. So, you are going to read what you have already filled in. For example, to start with, first block is written in RAM 1, and then second block is written in RAM 2. When this happens, concurrently you would have started this DCTQ, and from RAM 1 it is being read, and this is addressed by a counter created in the controller. And the controller is not an FSM realization as we have seen before in previous designs, it is a counter based design. You will see that it is very handy for where you need to address memories, registers in large number. So, counter based design will be very handy. So, this is a deviation from the routine designs. And now, once you have filled and given a start for DCTQ processing, what happens is this read address is applied to this RAM 1, let us say, and gets the very first row and into this X here, and note that the row has only 64 bits, that is what is applied here, and corresponding to this what we are going to do is we are going to evaluate CX matrix. So, all this structure, the architecture will have to reflect this parallel algorithm we have developed before, and it is same nomenclature is put at strategic points for you to grasp what they are. So, only remember that one row of the image only is being applied at one point of time. So, at every positive edge of this clock we will keep on changing a new row. That means to say it is pumped at a very high rate of the system clock. So, that is the beauty of the pipelining, and as I mentioned before, we have 45 stages of pipelining which we will be examining as we proceed further. And first thing is we want to realize CX, and this is as you can recollect, it is the first row of the C matrix and then multiplied by the first column of the X matrix. That is what we have seen before, that is what we are doing here at this stage. And every time the C row remains constant for the next 8 clock cycles, including the first one, and only the X is going to change from the first column, then second column, and so on, in order to create one complete partial product row of the matrix. That is what you had earlier, and that means you had to change this one 8 times. So, every clock this will keep on changing, and at every clock you are going to do the 8 multiplication at one time. That means you need 8 multipliers. So, that is what is here, and we have seen the multiplier design also earlier, precisely the same multiplier. Therefore, this also will not be covered here, and you remember it is first input is unsigned. We mentioned before this X, which is the image, is unsigned, whereas C is the cosine. So, naturally it calls for a signed number, and that is the reason why we are using 8U into 8S multiplier, and there are 8 multipliers, and nomenclature as say different ICs you can identify as U11 through U18, and you need the 8 pipeline stages here. As you recollect, all our multipliers earlier were 8 pipelines. So, there are 8 pipeline registers here. So, any data going here will manifest only after a delay of 8 clock cycles, and that is what is responsible for the latency. So, here in dual RAM also we have seen in RAM which is being called by dual RAM, there is 1 clock delay there because 1 pipeline register was used there, and another pipeline in the top level dual RAM itself. So, this contributes to 2 clock cycles delay. So, there is a 2 pipeline here and 8 here. We need to keep track of all this, and I hope you will keep the count. So, 2 here, 8 here, and next was adder. So, out comes the result which is nothing other than CX 8 products are available and they are designated as result 1 through result 8, and all of which need to be added, which we can use our previously designed adder, which is added 12s. You recollect that it is not registered. I mentioned therein that it is not registered for a particular reason. The reason is will be clear now. So that is because we have following register here, and what is the point in having a register here and one more register duplicating? So it is a waste of register there. So in order to avoid that, we dispense with the register here, whereas in the next stage you will see there will be a register, because following stage there is no register. So we have designed this also. In fact, we have designed all these 3 blocks. What we have not designed is this register, and you just keep track of this. This if you recollect, it will be 5 pipeline stages, 2, 8, 5, and here actually it is a group of 8 registers, and in fact there are 15 registers. When you go into Verilog code, we will understand why it is so. As basically to register all the partial product. First CX created one row of partial product P0, not P01 and so on up to P07. So all those will have to be registered, and each of this will be arriving at a different clock points. First clock you will get P00, second clock P01 and so on. So you have to keep track of all that, and then at appropriate time you have to register here, and there are registers designated as QR0 to QR7. Very first register is QR0, and that will be registered when the address for this one is given here, and this is derived from the controller. As I mentioned before, it is all based on counters, and second counter is invoked here, and it is a 3-bit counter, whereas the first is 5-bit counter here, 5 or 6-bit, I think 6-bit counter, right, of which we have used only the LSB portion, and let us see where we use the MSB. And here this is nothing other than address for the register what we want to have. So if it is very first P00, this address will have to be 0, for P01 it will have to be 1, and automatically all this controller, I mean counter etc. will have to run very synchronously. Even if you make one simple mistake, everything will be topsy-turvy, right. And these registers will be actually registered inside only with an enable control, and this enable control is the same as the enable control for the counter, which we will be seeing in the controller design. And this again is, there are 8 registers, so the data will go around all this only after 8 clock pulses it will emerge forth. So the total entire QR0 to QR3 is 7, which is none other than the partial product piece, and here will be available only after 8 clock cycles. So once with the arrival of the next clock, but we have already seen before, there is no relaxation as far as the input is concerned. Once the first block is processed, it does not wait, immediately it starts with the second process, and if you look at this, inspect this data bus here, you will see that there is incessant activity there. Every clock pulse some activity will keep on going, all of them are meaningful. Therefore there is no respite for the DCT processor all through, and only here there is little, in the sense that this will be available to you, this partial product, for 8 clock pulses, because unless this is stationary you can't compute the second partial product, which will take 8 clock pulses, right. So if you do not have duplicate registers here, say I said 15 registers, you can't accomplish this feat. So because the first register will be overwritten and you lose what you have stored, which we need for further computation, so it will be overwritten. So that we do not want that to happen, and that is why we need to be very careful about this design. Although the design is quite simple, we need to take extreme care. And so the next step is, what we have seen before is CX and one row of partial product only we have got here, and the total delay you remember is 2 here pipeline, and 8 here, 5 here, then 8 here. So this architecture continues here, and next is we need to have C and CT, and they are available in the ROM stored, and similarly we want to have a quantization table, that is also ROM, and in fact we have seen the design of both the ROMs earlier, and we pointed out it is inverse quantization which we are storing there when we dealt with this design, and that is precisely what we are seeing here. And for this, once again, this address, you remember that there were two addresses. One address is derived from counter 1, other now note that one, this address is derived from MSB of the same counter 1 there. So because we will have to not only address X here, but also get C simultaneously. Therefore the same counter is addressing both, right. So only difference is this is in LSB, means this happens more frequently than the MSB, and that is once in 8 times only, because you need to have all the entire, all the rows of the matrix for one value of one set of C, and repeat the same thing again in order to get partial product that we have seen. So this is quite simple, and counter 4 gives the address for the ROM queue, right. Out comes the quantization matrix value here. For example, if you give 0 here, out comes 8 here. If it is 1, it will be 16, and so on. So as per the quantization matrix we have stored here, and here also we do not really store the actual quantization matrix, but it is inverse, and that also a number of times more in order to improve the accuracy. And note that one, this also has latency here, here as well as here, 1 clock pulse latency or something, and but anyway this is a parallel process when compared to the other here. What we have done is earlier is evaluated partial product here, and that we feed in the second stage of multiplication. So for second stage of multiplication, note that we need a higher precision 11 here for this one, because QR0 to QR7 I have taken as 11 bits precision, and I have experimented with several bit precision and arrived at this one to give an optimum quality of the image, and in fact all through all the precisions have been arrived at after experimenting only. And so you also need another input, which is nothing other than CT. Now we have to multiply what we have earlier as partial product P, which is none other than QR here in the register that we have seen before. It's that is nothing other than CX matrix, CX one row of the matrix, and we need to multiply that row into the CT matrix in order to get the DCT. So we have to apply the CT here, which is none other than this same C ROM table that we have seen, and you need once again 8 multipliers as explained in the algorithm earlier, and designated as U21 to U28 here, and precisely the same thing you can see in the Verilog coding, and what all I have put here, the very same nomenclature I have adapted in the Verilog coding too, and all the signals, everything will be a 1-to-1 correspondence in the coding. And after this, what we have multiplied, and 8 results are there here, result 1 through 8, and all of this we have to add, and we need one more adder, which is 14 bit with registered output. This is what I have given as an assignment earlier, and hoping that you have done, and I am not going to show it anyway. I hope that you have already done that, and also you had to you are given assignment for this multiplier as well as this multiplier, and this multiplier is to create DCTQ out of DCT, and here this multiplier has this is nothing other than adding all this row into column multiplied here in order to get the DCT here. If you add, what you get is the DCT here, and DCT precision is 12 bits here, and this is as per the standards, and it is signed 2's complement form, and Q out is that ROM Q table we have seen here. This is the Q out, ROM Q. It gives the quantization value, and which we need to input to the multiplier in order to get DCTQ. DCTQ is actually a division of DCT by the quantization value, but division can be interpreted as a multiplication if you inverse the quantization value, and that is precisely what has been done here. In the ROM we have inverted the value so that we can use a multiplier there instead of a divider, that is all here. right. Once you multiply again DCT is 12 bits, that is the reason why it is 12s here, and this is just 8 bit precision, and once again a signed value is put, in fact unsigned is enough I think, yeah, it might be unsigned, okay, you can correct that one, and out comes DCTQ 9 bits here. So, what we have here before we wind up the architecture is we have the whole thing, you will see that it appears very complicated. So, you need to regulate the whole activity. So, you can do so only if you have a controller specifically designed for that, and you can see so many control signals here coming out of the controller, and plenty of other signals are inside this. When we look into the DCT controller, you will see more details here, and it calls for several counters of various bit precisions here as listed here. In fact, counter 5 is nothing other than address, this is nothing but the DCTQ address here. Address 0 corresponds to the DC quotient and all others are AC quotients, and DCTQ valid signal also will have to create, which will keep in step with DCTQ output. So, we will have to keep track, I mentioned keep track of all the pipelines, you have to keep track of all the pipelines, then only we will know when to activate this, and we will see a little more details later on that. And enable counter 2 was required for the DCT register, that for storing the partial product, that is what is here, and we also need R and W in order to switch from RAM 1 to RAM 2 in dual RAM, that is why this signal is here, and system clock for DCTQ processor is here, and you need a reset to reset the whole system, that may be internal registers which we need to reset, and in fact all the variables signals that we have inside will be reset by the standard always block, and you need a start in order to start the DCTQ processing, this is what I mentioned before and right at the beginning of explaining the signals, and you also need a hold signal, and ready is issued by the DCTQ processor, it is primarily generated here at the controller here. So, this completes the architecture, and before this we will once again examine how much delays are involved. So, here we saw the 2 pipeline here, 8 here, then you just add all that, 10 here, then 5 here, 15, then 8 here, 23. So, this delay need not be reckoned because it is a parallel affair. So, how much did we count? 23, and that is we are looking at only the data flow, right. So, and here once again 8, 23 plus 8, 31, then 6 here because register is involved. So, how much does it come to? 37, right, 37, and once again one more multiplier is there which is 8, so 45. So, out comes DCTQ only after 45 delay. So, every clock the whole thing is pushed one after another, you have seen just now the entire data flow, and this is what we meant by pipelining. You remember we have covered, and while designing multiplier we saw how a pipelining is, what the concept is. Now, we should appreciate better when we actually deal with the actual design such as a DCTQ. So, we have seen 45, we also need at intermediate points later on, we will come back to this later on. So, this completes the architecture which has a 1-to-1 corresponds with the algorithm. So, now next point is, say whatever processor we have designed for DCTQ, it cannot be a standalone, right, we will have to build further hardware, you have to put it in a PCB, and you may require other hardware, or even the host processor you may require, and that is why we assumed a PCI bus interconnection. So, it calls for a host processor as well as the DCTQ processor itself. So, we had to intercommunicate with them. So, and what is the way of communication? So, you need a sequence of operations for that. It says a step by step operation sequence of the host and DCTQ process are as follows. So, for the host what we need to do is, first the host will have to send the reset signal, and to initialize the DCT core, because there are so many registers inside, they will have to be initialized to different values, not necessarily 0, and so that is what is being done here. And at any point of time you can always apply the reset. So once you apply a reset and start again, latency will come into picture, so take care of that. If you do not want latency, do not assert reset only right at the beginning when the system is switched on, or deliberately when the whole JPEG or MPEG is initiated. So at that point only you need to reset, and thereafter do not reset, and probably after processing one frame, if you feel like, you can initialize once again, and if the need arises. Otherwise you can use the hold signal, and you can do away with dispense with the latency, and thereby you will speed up the processing considerably. So an 8 by 8 block of image data, 64 bytes, is written by the host processor into one block of the 64 byte dual RAM in the DCT processor, 8 bytes at a time via the data bus DI. After ascertaining that ready is set, all the BE bits may be simultaneously asserted, PCI compatible with PCI clock as input clock, and DI invalid must be asserted while inputting the image data. It is quite plain, does not need any explanation. And the next point is the host processor issues start to begin DCT processing. Start signal must be continuously asserted for continuous processing. If you withdraw that one and apply again latency will come into picture, that is the reason. And fourth step is the last step for the first one, host. And if ready signal is set now, so it will in fact ready will always be high, except that means it is always ready, DCT processor is always ready to receive the input image except for few clock cycles, right. If ready signal is set now, next block of image data is written into another block of the 64 byte dual RAM, otherwise you wait for that. This is the role of the host, and this wait can be either polled mode or interrupt mode as far as the host processor is concerned, preferably the latter. So there are two notes here. Steps 3 and 4, that the last two steps we have seen, are repeated for processing subsequent blocks in succession. So you have to keep on churning the same thing, and block after block you have to keep on writing into, and DCT queue will be processed simultaneously. The host asserts reset signal once at the beginning of processing normally. This is with the intention of eliminating latency. So with the exception of the processing of the very first block. Very first block has latency of 45 clock cycles, which we have seen just now, seen in the architecture, and subsequent blocks it will not be there, because every clock pulse it is actual data is being processed. And if you take a big picture such as what we have seen earlier, and we have some 1024 by 768, which will work out to be thousands of blocks, each block being 64 bytes. So naturally when compared to one frame wherein thousands of blocks are there, latency of 45 clock cycles is a negligible thing. Therefore I said you can even apply reset at every frame, even then it will not make any significant delay of processing. So however it may apply reset at any point of time, be it at the start of processing every frame, introducing latency for every frame, or when terminating the processing. Finally you wish to terminate the entire processing, image processing or video processing, then you need to do the assertion. And this is the role for the DCT processor, which are going to say, look into the Verilog code later on. And here if reset is set, initialize all the internal registers and terminate the current DCT processing. For example, it was already processing something, so the moment reset is applied, it will abandon the DCT processing and initialize itself, and select one RAM bank for the host to write the image block. So it is this is by the control R and W, and it does that. One bank is in read only mode for DCT processing, while the other bank is in write only mode for the host to write the image block concurrently. Set the ready signal. So so immediately we set the ready signal, so that next block can be written fast, and note that it is just 8 clock cycles you need for writing by the host. So rest of the time it can attend to other cores. So second point is if start is asserted, begin processing, that is a DCTQ processing, you start here, otherwise wait. So, assert ready signal for the host to write into the other RAM bank concurrently. So, and otherwise if you do not assert the ready signal, you can't host cannot write, that is why you have to do it as quickly as possible. Then start computing DCTQ. The DCTQ questions are issued at DCTQ 80, this 9-bit pins, valid at the positive edge of clock. This clock is the system clock for DCTQ, and with DCTQ valid, signal asserted. So, when DCTQ becomes valid, simultaneously DCTQ valid also goes high, both simultaneously. So, you can this will be valid at the positive edge of the clock. So, after one clock delay only you can register in any other subsequent processing. So, which will still be holding good, right, because it changes value only at the arrival of the clock. So, right at the fag end of the clock also you can register to the into the external world, external to DCTQ processor. DCTQ questions are issued at these pins valid at the positive edge of clock with DCTQ valid asserted after latency of 45 clock cycles. This is what we have seen before, explained earlier. DCTQ valid signal is continuously asserted as long as the processing continues without a break, and address is valid when the DCTQ is valid, and DCTQ is issued every clock cycle from 46th clock cycle onwards, which we have seen the recent, and 64 questions are issued per image block. So, one block of image contains 64 pixels and 64 questions are coming. So, that means it is equivalent to saying that it is not one-to-one correspondence between pixel and DCT coefficient. What all we say is 64 questions, 64 pixels. So, we can say one-to-one correspondence we have, and every clock one coefficient is issued. So, that is therefore, it is equivalent to saying that one pixel is processed every clock, and this is how we justify how it is processing one clock at one clock rate, right. And we have seen the entire architecture how it was doing as well as the algorithm, and explained how it was outputting at every clock. It is doing so for simple reason that every clock we are applying the input data. A fresh data is applied every clock, which we have already seen at the CX matrix input of the first multiplier, and therefore, whatever we apply will have to come out. So, at the same rate. So, otherwise everything will go completely in disarray, and 64 coefficients are issued per image block. This implies that one image block is processed in 64 clock cycles, that is what we have explained just now, 64 coefficients in 64 clock cycles. So, and once again 64 pixels are there. So, you can say that one pixel is processed at the rate of one clock cycle. The first coefficient, that is address is 0, is called the DC coefficient, and others as AC coefficients, others are 63 in number. So, we have a note here for this, say step 2, that step 2 is here, that is what we have seen here. This is repeated DCTQ computation, that is what. So, we had to keep on repeating this block after block, continuously process as long as start is kept asserted and reset or hold are not active. If there is a hold, this will be suspended. If it is reset, the whole system will be reset, right. So, and one more thing is not present, I mean of course, it is covered in this item 2, start must be asserted there, and this completes the interface, the intercommunication between the host and the DCTQ processor. If you have any questions, we can answer this your question pertaining to what we have covered so far, because we are going into the Verilog codes shortly. So, if you have any question, can I ask?
Actually, for the first computation, 45 clock cycles is the latency, isn't it?
Yes.
Similarly, when you stop the computation, shouldn't you give 45 clock cycles for all the operations to be over and the result to be available at the output?
Yeah, but that will be taken care of by that DCTQ valid, right. Whatever you have given outcomes, that one. So, DCTQ valid signals when it is going, I mean when it goes low, it means the whole thing is over, right. and it is also available by inspecting the address bus. So, ADDR we have seen, if it is 63 you can very easily see that it is going to be over. You have another question?
Yeah, this is very basic probably image processing question. Why did you choose a 8 into 8 matrix? Why couldn't you have chosen a 16 into 16 matrix or a 4 into 4 matrix?
And that is a good question. First obvious reason is that is what the standard prescribes, an 8 by 8, but that is only an superficial statement answer which may not satisfy you. The real basic thing behind this is, see, for example, this is the realization of DCT, which is 8 by 8 matrices, 3 matrices, and we have seen that computation world is very high. As in your question, suppose we have used 16 by 16, what will happen? This will be huge matrix, each of them. Just imagine multiplying, how many multipliers you require? What will be the chip area? It will be exponentially increasing. So, it will soon become impractical. If it is instead of 8 by 8, had you used 16 by 16, it would have risen. I mean, chip area would be too impracticable. And on the other hand, if you go for 4 by 4, and you will have quality of the image deteriorating. So, there is actually some of the textbooks on image processing, they give a plot for various transforms, not only DCT, for KLT and DFT and so many other Hadamard transforms. For all of them they give a graph saying, I mean, plot that graph is least mean square error. Error is arising by applying DCT and then followed by quantization, then IQ, IDCT, that is a reconstructed image. So, the error arising going through all this is you extract the mean square of that. So, if you plot mean square versus this number of blocks, say 4 by 4 or 8 by 8, 16 by 16, you will see that it has a least mean square. I think it goes something like that. If vertical axis is least mean square, and this is number of blocks, for example, first one is 4 by 4, then 8 by 8, 16 by 16, you will see that the curve goes something like this, and it has it touches for 16, no doubt, as you mentioned, for 16 by 16 or even beyond, it goes to the rock bottom. So, that is the mean square. So, from quality point of view, that is the best, but at what cost? I mean, skyrocketing chip cost, because more the multipliers, more the chip area. Just now we have seen 8 by 8 itself, 8 plus 16, had you put 16, 16, what will happen? 16, then 16 multipliers here, then another 16 there, and so on. So, more it is, more the chip area. So, but it gives a better quality, but what is the quality that you get over and about this 8 by 8? It is only a small fraction, because it is for 8 by 8 itself, this curve almost dips to the minimum. So, it is only a small dip further, right. This does not warrant, that is the reason why they have standardized on 8 by 8. Thank you.